The seething face of a star. The only star in the universe we can glimpse like this. That star is the sun. An inferno spewing energy, heat, and light. Without our local star, just 150 million kilometers distant, Earth would be a lifeless planet. The sun is hub of our solar system. These are its outer limits, a swarm of icy particles stretching a third of the way to the sun's neighboring star. Like the planets farther in, everything orbits the sun. Pluto with its tilted orbit, Neptune and Uranus, great spheres of gas. Two more, Saturn with its rings, and mighty Jupiter. Little red Mars and beautiful blue Earth are first of the rocky inner planets, then Venus, and finally scorched Mercury, all captive to the gravitational pull of the sun. The core of the sun is a nuclear reactor. At 15 million degrees Celsius, hydrogen is converted into helium in a continuous chain reaction. As nuclei of hydrogen fuse to produce nuclei of helium, there's a tiny loss of mass. That matter is unleashed as energy. Each second, our star loses 4 million tons of mass, energy that will keep the sun blazing for another 5 billion years. Overall, the sun is no denser than yogurt. At the white-hot core, however, it's 10 times denser than lead, and energy released there takes at least 100,000 years to reach the surface. That same energy as sunlight takes just 8 minutes 20 seconds to reach us. It powers our planet. Our fossil fuels are stored sunlight. The sun drives our weather systems, grows our crops, and sustains almost every form of life. By passing a sunbeam through a triangular glass prism, we learn much of the sun. White light becomes a spectrum of color and dark lines. They reveal the solar composition: 70% hydrogen, 28% helium, and 2% heavier elements, such as iron. Those heavier elements are inherited from a supernova. The death of a giant star, its shockwave interacted with this cloud of gas and dust. As it slowly rotated and flattened, the center collapsed and a nuclear furnace fired up. 5 billion years ago, our sun was born, and from the surrounding disk, the planets began to form. Our own planet would fit inside the sun over 1 million times. It's so big, the sun comprises 99.8% of the solar system. A ball of incandescent gas held together by gravity. This is the solar surface, the yellow photosphere. At 500 kilometers deep, it's the wispy shell of gas that produces sunlight. Real pictures of the photosphere, bubbling granules, each the size of Texas. Gas rises through the granules, cools, and descends again through the separating lanes. Time-lapse of the rotating sun reveals sunspots. They come and go over several days, and one could swallow Earth. They're cooler than the surrounding photosphere, whose temperature is almost 6,000 degrees. The dark center of a sunspot, the umbra, is just 4,000 degrees. Its warmer periphery, the penumbra, is 5,300 degrees. This comparative coolness is caused by local magnetic fields. Their intensity suppresses currents, bringing hot gases from the convection zone below. Through an 11-year transition, a spotty sun can become virtually spotless. The cycle is closely linked with the vast magnetic field that swirls and loops through and about the sun. Every 11 years or so, the field reverses as the magnetic poles flip. 11 years on, it'll happen again. Since the sun isn't solid, the surface spins at different speeds. The equator rotates once in 25 days. At the poles, it's 34. This tangles and distorts the magnetic field. From maximum solar activity, X-ray images show the cycle through minimum activity, when there are few sunspots, with a return, as the spots increase, to maximum activity. Again, this is solar minimum. And here's solar max. Surface activity in the yellow photosphere orchestrates the show above in the red chromosphere. This inner solar atmosphere erupts with searing gas. A prominence arches into space. Billows of gas sweep along magnetic force lines. Prominences lick hundreds of thousands of kilometers, fueled by magnetic surges beneath. When the moon covers the sun at a total eclipse, the corona is visible by naked eye. This rarefied outer atmosphere is far hotter than the chromosphere and photosphere below. And it displays magnificent loops of electrified gas. These satellite pictures show the loops curving round magnetic force lines. They can span 30 times the diameter of Earth. A mysterious energy source at their base heats them to 2 million degrees. But solar flares are the most violent convulsions. A single flare can release the energy of 1 billion megatons of TNT. This is one of the most powerful. Here it is again, erupting near a group of sunspots. It triggers a coronal mass ejection, particles hitting a space probe millions of kilometers away. Twists in the magnetic field are the likely cause of flares and their mass ejections. Between these eruptions, the sun emits a steady stream of tenuous gas and electrically charged particles, the solar wind. Normally it blows at up to 400 kilometers a second. But at the time of flares and mass ejections, it becomes a storm. We can't see it, but instruments detect it. The sun throbs in regular 5-minute beats. The cause is sound waves generated by pressure fluctuations deep inside. They provide scientists with an audio picture of the interior. Trapped and bouncing within, the sound waves vibrate the surface in millions of patterns. As with the life it nurtures on Earth, the sun, like all stars, will die. In 5 billion years' time, hydrogen will run short. The balance of radiation pushing out and gravity pushing in will be gone. The sun will grow. From a diameter of 1.4 million kilometers, it'll expand to perhaps 200 times that size. Mercury will be consumed. Then Venus. The sun won't quite reach Earth, but our planet will be a cinder, devoid of oceans and life. Puffing off shells of gas, with hydrogen and helium spent in the core, the sun will become a red giant. Finally, its outer layers stripped and its core exposed, the sun will collapse to the size of Earth, a white dwarf. As it cools and dims to become a black dwarf, our solar system will be left cold, dark, and dead. Caught in time-lapse, the closest planet to the sun, in transit across the sun, baked little Mercury on the inside track. To understand Mercury, we return to the early solar system. A disk of gas and dust rotates around the newly fired-up sun. Hot and dense at the center, farther out the disk is diffuse and cool. Close to the sun, tiny particles condense, heavy materials with a high melting point. Beyond, grains are lighter and icy. Particles begin to clump. And the great disk starts marshalling into rings. Everywhere, collision and aggregation. Grains grow as big as basketballs, houses, mountains. And as they grow, so does their gravitational pull, offsetting the tug of the sun. Rings in the disk are increasingly defined, and within them, mini-planets are forming, so-called planetesimals, constantly growing as they sweep up debris. But it's still a mayhem of impact and assimilation. The bigger the body, the stronger its gravitational pull, and the more it grows. Thus do the planets shake out. In the farthest reaches, great spheres of gas riding vast and lonely orbits, but closest to the sun, solid little planets. Debris remaining between the orbits is blown away by the solar wind. The veil is lifted on this empire of the sun. And the sun still rules some 5 billion years later, with dense little Mercury the closest subject. Mercury, Venus, Earth and Mars are the rocky inner planets, the terrestrials, where the heaviest elements condensed. Jupiter and its fellow giants are balls of gas. They condensed in these cold outer regions from lighter elements. With the sun just 58 million kilometers away, Mercury is scorched and irradiated as no other planet. It's named after the messenger of the gods, and why not? For the ancients saw the sun as a god. Mercury is the smallest inner planet. Earth is 18 times as massive. Compare their diameters. Mercury is less than 4,900 kilometers. Earth is over 12,700. And they've different attitudes. Earth tilts. Mercury doesn't. Twilight on Earth, with Mercury on the right and Venus above. As they move through their orbits, they're never high in our sky. Mercury is the most difficult to see, barely clearing the horizon at dusk and dawn. A change of perspective shows why. From Earth, we see only part of their tight solar orbits. Venus, the outermost, orbits in 225 days. Mercury in 88. Mercury crossing the sun. Such transits occur 13 or 14 times a century. We see them because Mercury, just like Venus, lies between us and the sun. (1973). Blast off for Mercury. The mission is Mariner 10. Using the pull of Venus as a push towards Mercury, the craft was the first to use gravity assist, now a common technique. 2 months later, Mariner skimmed Mercury at just over 700 kilometers. There were 3 such flybys. They yielded a photographic feast. Here was a pristine record of the early solar system, the whacks and smacks that cratered this barren little world. Upper right is the Zola crater, remnant of an impact so mighty that ejected material dug these mini-craters. These craters could be in the highlands of our moon, another lifeless desert. From upper left come the streaks of a ray crater, the imprint of an impact on older terrain. Mercury has basins and less cratered regions like this. They indicate a younger surface, formed in a volcanic epoch when lava flowed. Great cracks betray a crust that has cooled and shrunk. Mercury has a mind-boggling calendar. Its day, sunrise to sunrise, is twice as long as its year. See how slowly Mercury spins as it circles the Sun. Watch the arrow. In a single orbit, the planet turns only 1.5 times. Earth, by contrast, would spin 365 times. The result is that Mercury's day lasts 176 Earth days. Mercury's year is just 88 Earth days. And it becomes stranger. From the surface of Mercury, during its long, long day, the Sun shrinks in the sky. Nothing to do with the Sun, all to do with the planet's varying distance from the Sun. Mercury has an elliptical orbit, and it produces an even weirder effect. Each time it passes close to the Sun, Mercury speeds up and slows again. The consequence on the planet is a double sunrise. And it happens only when Mercury is closest to the Sun. Early in its history, Mercury may have been struck by a large planetesimal. Such an impact could have blown off the planet's outer mantle. That would explain, relative to its size, Mercury's huge iron core. It's 70% of volume, twice the proportion found in other terrestrial planets. There's no doubting the impact that happened here. With rings of mountains curving towards the left, this is one side of the huge Caloris Basin. The cause was another planetesimal. 4 billion years ago, it gouged a crater 1,300 kilometers wide. Splattered later with these smaller craters, the basin had probably filled with lava. The mountainous rim of Caloris, lava fields to either side. Volcanic activity lasted 1 billion years, but for the past 3 billion, it's been quiet. Lava plains surrounding the Caloris Basin. Caloris means heat. Well named, for the basin can be Mercury's hottest spot, with a daytime peak of 450 degrees Celsius. At night, temperatures plunge to minus 180. And radar mapping suggests permanent ice on Mercury. Radio telescopes in the United States and here in Puerto Rico hint at the paradox. If it's true, ice could only survive on Mercury in deep craters at the poles. There, perpetually shadowed from the Sun, could be the icy deposits of comets. Most of our knowledge of Mercury is from Mariner 10 in the mid-70s. And that left more than half the planet, the blank areas, still to be photographed. But new missions are planned. This is Bepi Colombo, a probe to be launched by the European Space Agency. Like Mariner, it will slingshot via Venus. So much is to be gleaned from Mercury, with its wispy atmosphere of helium and a surprisingly strong magnetic field. The Americans plan flybys with this messenger craft to better know what shaped this planet. Mercury's surface is the history of our solar system from the earliest times. Billions of years ago, this could have been Venus, a planet of oceans evolving microbial life. Today, this is the reality, a lifeless world with a dense and choking atmosphere and temperatures to melt lead. Venus is Earth gone wrong, a runaway greenhouse effect, a planet resurfaced as molten lava spewed from within and covered everything. Venus, always shrouded in cloud, is second planet from the Sun. orbiting at a distance of 108 million kilometers. And with a diameter of just over 12,000 kilometers, Venus is almost as big as Earth, often dubbed a twin. But few twins are so different. Earth is clear-faced and temperate. Venus is hell, where clouds blow right round the planet in 4 days. From Earth, Venus is by far the brightest planet. Through a telescope, cloud obscures any features, but interestingly, Venus has phases like the Moon. At its closest to Earth, the planet displays a thin crescent. It increases as Venus moves away. But when more of the face becomes visible, so Venus, still moving away, seems to shrink. For earthly observers, Venus lies above Mercury. Their orbits keep the planets close to the horizon. But there's no missing Venus, big and brilliant, just after sunset and immediately before dawn. Back away, and the horizon hugging is explained. Venus and Mercury have tight solar orbits. Venus on the outside takes 225 days to circle the Sun. And every so often, Venus can be seen crossing the Sun. In 1769, commanding his ship the Endeavour, the explorer James Cook sailed to the Pacific to observe such a transit, in Tahiti. His observations were set against measurements taken elsewhere. Simple trigonometry revealed the distance from Earth to the Sun. Thus did Cook help initiate the measurement of the universe. In scaling the cosmos, the distance from Earth to the Sun is a basic unit. Today, transits of Venus are mere curiosities. They occur in pairs every century or so. Venus, named after the goddess of beauty and love, has long been a mystery, and speculation has been wild as to what her cloudy veil concealed. Some imagined a planet covered in swamps, exotic plants sprouting from the morass. Others believed it was a desert, rocky, dusty, and baked. Another notion had Venus awash in soda water, oceans bubbling carbon dioxide into the clouds. As so often, fact is stranger than fiction. The unveiling of Venus began in 1961 by radar. From Goldstone, California, signals were bounced through the Venusian clouds. For the first time, we had echoes from another planet. And the news was that Venus rotated incredibly slowly, and in the opposite direction to Earth. The reason? Possibly a giant planetesimal had hit Venus, altering its tilt, even flipping it over. In 1970, the Russians soft-landed a probe. These are its pictures, from a surface where the sun never penetrates. A brutal landscape strewn with slabs of volcanic rock. Conditions so hostile, the lander frazzled in minutes. The atmosphere is like soup, over 90 times denser than Earth's. It blankets the planet, trapping heat. At 475 degrees Celsius, Venus is the hottest planet. Next, by radar orbiter, the Americans imaged Venus. Most was rolling plains, the blue, with 2 highland areas or continents in yellow and red. Then, using side-looking radar, Russian probes mapped the northern hemisphere. The detail was a breakthrough. Here it is as a computerized flyover from the 1980s. The region is Ishtar Terra, highlands the size of Australia. By the early 90s, improved radar enabled America's Magellan spacecraft to scan Venus as never before. Almost 99% of the surface was mapped. Here, stripped of cloud, the lazy rotation is revealed. Venus spins just once in 243 days. Earth does it in 1. Mapping completed and reacting with wobbles, Magellan began measuring tiny fluctuations in gravitational pull. It was a glimpse beneath the surface. Red and yellow indicate high density, blue is low. With a topography map superimposed, there's an almost exact correlation. In other words, mountains pull harder than plains. Thanks to Magellan, we fly the planet, first to its highest point on the continent of Ishtar Terra, and now south towards the larger highland region, Aphrodite Terra, a continent the size of Africa. With heights exaggerated and color guessed at, this is nonetheless an accurate spin through the vast canyons of the southern uplands, the Chasmata. To the east, and still in Aphrodite Terra, a great volcanic plateau. Here, Mart Mons, a massive volcano, stands 5 kilometers above the mean elevation of the planet. Unique to Venus are coronae like this. There are hundreds, caused probably by hot magma trying to push through the crust. Venus is the most volcanic planet in the solar system. 3 impact craters. They're less common on Venus compared with Mercury or the Moon, because lava constantly resurfaces the terrain. Also, after hitting the thick atmosphere, small missiles burn up and larger ones make less of an impact. Beyond a mountain range to a group of pancake domes, each 25 kilometers across and 750 meters high. They're probably upwellings of lava depressed by the weight of the atmosphere. Venus has been erupting for possibly billions of years. Sulfurous fumes adding to the toxic atmosphere, lava relaying the surface. It may still be erupting today. Magellan has revealed volcanic shields and lava flows that make up 85% of the surface. In planetary terms, this is a young landscape. The average age, just 500 million years. So what befell Venus? Has volcanic activity slowly oozed lava? Or did some global catastrophe completely renew the surface 500 million years ago? This is an artist's impression, for those Russian snapshots are still the only real pictures of the surface. In a searing and crushing atmosphere of 96% carbon dioxide, it's hard to imagine a human dropping through these clouds. Like Earth, far enough from the sun for life to take hold, 4 billion years ago, Venus could have had oceans, continents, and simple life. But the young planet was dangerously close to the sun. Earth is at the center of the habitable zone, Venus at the inner edge. So as the sun matured and its luminosity increased, Venus heated up. The vapor of oceans boiling dry may well have turned Venus into a suffocating, smog-ridden greenhouse. Earth had lost its twin. Look at Earth from space, and there's no sign of life. Our beautiful planet is just that, a symphony of color and form. Some color is false to enhance geological features. But where are we? Look closer, and there are the works of humankind. The city of Boston, with its airport and harbor on the northeast coast of America. But climb higher, and we disappear. From here, who would know Earth is home to 6 billion human beings? It may be planet Earth, but 2/3 of the surface is water. Compare this seascape with the barren terrain of neighboring worlds. Our oceans teem with life. Simple organisms probably first appeared here. Eons later, evolving lungs and limbs, life crawled ashore. Today it populates 6 continents, with one species evolving to dominate: Homo sapiens. In the 11,000 years since the last ice age, we've developed agriculture. Allowing few to feed many, it's the basis of civilization, freeing others to be artists, teachers, scientists. Not only has farming changed the landscape, but cities have too. Here's Chicago spewing pollution into Lake Michigan. As no other species, we've changed the environment and eagerly burnt non-renewable resources. Volcanic eruptions are symptoms of Earth's hot interior. Through vents in the crust, lava releases heat lost from the core as it slowly solidifies. Earth's crust is like a cracked eggshell. The cracks are boundaries of great plates, and where plates interact, there are earthquakes and volcanoes. But the greatest consequence is continental drift. Riding on partially melted strata in the upper mantle, this is how plate movement has changed the map of Earth during the past 500 million years. As plates crashed together, mountain ranges grew, like the Alps, where Italy hit Europe, and the Himalayas, where the Indian subcontinent collided with Asia. And where plates have pulled apart, huge fissures appeared, as here in the Dead Sea Rift Valley. Earthquakes and volcanoes mean plates are either pulling or pushing. They move at between 1 and 10 centimeters a year. And the process continues, whether in the oceans or from billowing peaks. Of the 4 inner planets in the solar system, Earth spins fastest, a rotation that gives us night and day. It means the sun appears to move across the sky. But the sun's not moving. Earth is turning on its axis. A 24-hour cycle that affects our weather, as the changing angle of the sun heats us and cools us. If our planet had an upright axis, the length of day and night would always be the same, whether at the equator or north and south of the tropics. But Earth is tilted at 23 degrees. That means day and night vary through the year. As we orbit the sun, the angle at which sunlight strikes us changes a little day by day, and it causes the seasons. Here, as the northern hemisphere tilts away from the sun, it's winter. Days are short, nights are long. 6 months later, when the north tilts towards the sun, it's summer. Days are long, nights are short. The reverse is the case in the southern hemisphere. Most of our weather patterns depend on a simple fact. Hot air rises. And it's the sun that drives those patterns. As it heats the oceans, evaporation occurs. Air laden with water vapor rises. And as it cools higher in the atmosphere, clouds form. Rising air, where there's cloud, causes low pressure. Falling air, where it's clear, causes high pressure. Air at high pressure always moves towards low pressure. This creates the winds that blow around our planet. About the equator, where heat from the sun is greatest, masses of cloud, heavy with vapor, form high in the atmosphere. Here they're pictured from space. Thunderstorms and torrential rain pervade the tropics and nurture the equatorial rainforests. Driven by the intensity of the sun, larger storms whirl from the tropics, cyclones, typhoons, and this a hurricane off the United States. On land, there can be dreadful damage. Global weather works like this. At the equator, where the sun is intense and air rises, pressure is low. At the poles, where the sun's rays are weak and air falls, pressure is high. Between the two, in the northern hemisphere, air falls just north of the tropics, but it rises farther north in the moist temperate regions. This creates three engines of circulating air. The effect over Africa is lush forest at the cloudy equator and desert in the clear Sahara. Europe is cloudy and damp. Here, a dust storm has blown into the Atlantic. To the right, the vast Sahara straddles this arid high-pressure zone. In Europe, cloud scuds from the ocean. The Atlantic seaboard is especially wet. It's changeable in this normally low-pressure zone. But in high-pressure polar regions, it's relatively cold and dry. The Sun isn't at a constant distance from Earth. Our near-circular orbit is sometimes more elliptical, but the change is slow, a cycle of some 400,000 years. This effect, however, a wobble of our axial tilt, occurs over 26,000 years. And this one, a change in tilt from 22 to 24.5 degrees, happens during a cycle of 41,000 years. Many scientists believe these effects contribute to ice ages. The last one ended just 11,000 years ago after a grip of 90,000 years. It's no Hollywood fantasy that Earth will suffer another ice age. For our grasp on this world is tenuous. Our cities, our crop growing, are but scratches on a fragile planet. Earth is a lucky place. We have air to breathe because green plants evolved to produce oxygen. They emerged thanks to water and Earth's fortuitous distance from the sun. This wonderful planet is precious and, in cosmic terms, precarious. Such an impact might have seeded our moon. When Earth was just 50 million years old, it was probably struck by a body the size of Mars. But there's a twist to this intriguing theory. The collision was a glancing blow. 2 days later, the impactor returned. This double whammy, a bad weekend on Earth, could well have blasted enough material into orbit to form the moon. Most likely, our planet had received the luckiest one too. Quickly, in no more than a year or two, a molten moon was orbiting a molten Earth. And at 20 times closer than today, the moon loomed huge in earthly skies. The gravitational pull between the two was immense. But most importantly, the moon's rotation became captured. In one orbit of Earth, the moon turns once on its axis. In other words, the moon always presents the same face to Earth. And here is that face. From Earth, we never see the far side of our partner in space, albeit a junior partner. For the diameter of the moon, at 3,500 kilometers, is 1/4 that of Earth. At a distance of some 384,000 kilometers, the moon takes 27 1/3 days to orbit Earth. As it does so, the moon appears to change shape, what we call lunar phases. To understand them, we must view Earth and Moon from space. With the sun shining from the right, exactly half the moon is always lit. It's reflected sunlight, because the moon has no light of its own. But from Earth, as the moon swings round its orbit, we see varying amounts of that half-lit surface. When we see only the dark side, it's new moon. When we see all the lit side, it's full moon. Remember, the shadow is cast by the moon, not by the Earth. To many, the moon is both familiar and strange. What, for instance, are the dark patches, those so-called seas? This one is Mare Humorum, the Sea of Humours. And this, a great bay opening into the Sea of Showers, Mare Imbrium. Here, the northern rim of Mare Imbrium, with, above, the dark crater Plato, and to its right, Alpine Valley. Mare Imbrium is the dark terrain on the right. Contrasting with the brighter uplands, it's 1,300 kilometers wide. But mare aren't oceans, they're basins gouged by impacts. Here comes the big one that formed Mare Orientale. Post-impact, lava welled from beneath and cooled into a sea of dark rock, a mare. Such major impacts suddenly stopped 3.9 billion years ago. Nearly a billion years later, volcanic activity also ceased, as the moon's interior cooled. But smaller impacts continued to pockmark the lunar surface. Craters proliferated. The Copernicus crater. A quartet of craters. Clavius, with younger craters inside. This moonscape records impact after impact. No water or wind erodes them. No atmosphere lessened their force. All that erodes old craters are new craters. The youngest craters are surrounded by splashes of bright ejecta, such as this. Like pebbles hitting mud, ray craters are the brightest features on the moon. Around the rims of big impact basins, mountains are thrown up. These are the Apennines. The moon has clefts and rifts and winding rills like this, channels where lava once flowed. With 81 times more mass, our planet is very much the senior partner in the Earth-Moon system. Lunar gravity is 1/6 that of Earth. Witness the antics of the 12 Apollo astronauts who landed there over 30 years ago. And with no air resistance, they showed how a hammer and feather fell at the same speed. In this magnificent desolation, as one astronaut put it, temperatures can reach 120 degrees Celsius by day and minus 160 at night. Astronauts became geologists during the landings. 6 Apollo missions collected rock and soil samples totaling 380 kilos. To speed the process and extend sample range, moon buggies were used during the last 3 landings. It wasn't all flags and footprints. The last samples were carried home in 1972. Analysis revealed they were very dry and either volcanic or the product of impacts. They were like rocks in Earth's upper mantle. At the end of each mission, landers were crashed back into the lunar surface. The moon rang like a bell. It indicated pulverized rock, reverberating just beneath the surface. The moon's interior is probably solid, its core metallic. But that core is much smaller than expected, 1/5 of the lunar diameter. By comparison, Earth's core is more than half the width of our planet, a disparity that suggests different origins, which backs the notion that the moon was born of an impact with Earth. When it formed, the moon was 22,500 kilometers from Earth. Today, it's nearly 20 times as far, and getting farther. We know through lunar laser ranging. Apollo astronauts left reflectors on the moon. From this instrument in Texas, scientists with pinpoint accuracy measure the transit time of laser pulses bounced from the reflectors. This reveals the distance of the moon to within a centimeter. Currently, it's some 384,000 kilometers away. and it's receding at 3 centimeters a year. The cause is tidal drag, the gravitational pull exerted by the moon on our oceans. Although the sun has a little influence, the moon, shown symbolically here, causes a tide to rise in just over 6 hours and to fall again in the same time. Twice a day, around the globe, tides rise and fall as the moon tugs on the oceans. They bulge at either side of Earth and are pulled ahead of the moon because of the faster spin of our planet. But tidal drag is slowing that spin, and our day is getting longer as moon and Earth pull farther and farther apart. The moon has another effect. It keeps Earth on an even keel. But suppose we lost the moon. We'd be all over the place. With the moon no longer pulling on the bulge at Earth's equator, axial stability would be gone. Over millions of years, we'd wobble chaotically, tilting from 0 to 85 degrees, and our climate would be shot. Imagine the nightmare as we keeled over. Ice would girdle the equator. For the first half of the year, ice would spread far into the southern hemisphere. 6 months later, the northern hemisphere would be enveloped, as ceaseless sunlight bathed the south. This could be Egypt. The Sahara, a howling waste of icy blizzards. Antarctica, a blazing desert. It may sound science fiction, but it's not. For in a billion years' time, when the moon is far gone, Earth will wobble. Olympus Mons, 3 times the height of Everest. Olympus Mons, 50 times the volume of Mauna Loa, Earth's biggest volcano. Olympus Mons, greatest volcano in the solar system. These cliffs alone tower 6 kilometers. From the surrounding terrain, Olympus Mons rises 25 kilometers. The base is as wide as the state of Colorado. This is the Red Planet, and despite a chain of enormous volcanoes to the east, the supreme feature remains Olympus Mons. Welcome to Mars. And here's the weather. From minus 100 degrees Celsius before dawn, frost and mist disperse in the morning. The sky is pink with Martian dust. Winds are light and variable. At midday, it's fine and clear, with an afternoon high just above freezing. But as sunset approaches, ice clouds appear and temperatures plummet. Mars lies 228 million kilometers from the Sun, the 4th planet out. One orbit takes 687 days. A Martian year is almost twice as long as a year on Earth. With a diameter of less than 6,800 kilometers, Mars is little over half the size of Earth and 1/9 its mass. Both have similar axial tilts and rotation speeds. To us, the Martian day is a comfortable 24.5 hours. Mars is the world on which next we'll walk, and we're getting familiar. The north, smoothed by the flow of lava plains, has the younger surface. The south is more rugged, heavily cratered from old impacts. Roughly marking this divide is the Great Rift of Mariner Valley. It would stretch coast to coast across the United States, the largest geological fault in the solar system. Approaching again from the south, we turn west for a sweep down the valley. At a maximum 7 kilometers deep and 600 wide, this is the grandest Grand Canyon. West of Mariner, we climb towards the Tharsis Ridge and 3 volcanoes. First, Arsia Mons. Then, Pavonis Mons. And finally, Ascrius Mons, summits rising over 20 kilometers. This craft, Mars Global Surveyor, has revolutionized our view of the red planet. By bouncing pulses of laser light from the surface, it's mapped the contours of Mars. Here in false color, red and white indicate highlands. Lowlands are in green and blue. The deepest blue represents the deepest depressions. The very deepest is the imprint of a huge impact. Hellas, whose basin floor is 5 kilometers deep. And picked out in white, Olympus Mons and the triple volcanoes of Tharsis. Today it's too cold for water to flow on Mars, but it probably did when these peaks erupted. Rising from the depths, hot magma may have melted subsurface ice, unleashing vast quantities of water, flooding the terrain. Beneath ash and lava to the east of Tharsis, Global Surveyor has imaged an ancient flash flood channel, here in blue. Mars abounds with evidence of floods. Etchings of catastrophic outflows. Dug into the surrounding plain, this channel is 3 kilometers wide. Compared with the arid planet of today, early Mars may have been warmer and wetter. A great sea, called Oceanus Borealis, could have filled much of the northern hemisphere. The reason may have been global upheaval, volcanic gases thickening the tenuous atmosphere, sending temperatures soaring. It may even have rained. As eruptions melted subsurface ice, Mars could have flowed with water. Are these layered rocks the relics of lakebed or seafloor? If so, why did the water disappear? Probably volcanic shutdown. Eruptions no longer replenished the atmosphere. It leaked into space due to weak gravity. The seas ran dry. Residual water froze beneath the surface. These tiny volcanic cones, less than a kilometer across, are further clues of a watery past. We see similar features on Earth, where geothermal springs vent through swampy water. Mars today is a freezing waste. The only visible water, polar ice. At its smallest in summer, this is the southern ice cap. It expands in winter. The northern cap is slightly darker because, when it grows, there's more dust in the atmosphere. 5 kilometers deep, scientists forecast that if both ice caps melted, the entire planet would flood to a depth of 10 meters. The elliptical orbit of Mars has quite an effect on its seasons. In the north, when the sun is closest, winter is short and mild. Summer, when the sun is farthest, is long and cool. The north has moderate seasons. In the south, they're more extreme. When the sun is more distant, southern winters are long and bitterly cold. Southern summers are short and relatively warm when the sun is closest. Most of Mars is a dusty desert, red due to the iron oxide. These are trails of dust devils, whirlwinds whipped from particles, finer even than talcum powder. Major dust storms can last weeks and blanket the planet. Since life depends on it, evidence of water remains the great quest on Mars. Here, grooves run down the slopes of a great valley. They're recent clues, possibly of short-lived cascades, released from an exposed layer of rock just beneath the cliff top. With water the objective, an American probe, Mars Odyssey, slots into Martian orbit. The mission is to scan the planet for signs of water ice just beneath the surface. Penetrated by cosmic rays from space, the surface throws out gamma rays and neutrons. They reveal subsurface elements. If there's hydrogen, it signals water, water locked up as ice. Sensing hydrogen, and revealed in dark blue, Mars Odyssey has detected vast reservoirs of underground ice, especially round the poles. In 2003, a new phase of Martian exploration. The European craft Mars Express deployed the lander Beagle 2, but as descent began, contact was lost. Undeterred, Mars Express surveyed the planet from orbit in high-resolution stereo. A plateau rising 3,000 meters. A crater 55 kilometers wide. Top shot of a volcanic summit. Hard on the heels of Mars Express, the Americans successfully landed Spirit, the first of 2 rovers. It may look unremarkable, but this is the real surface of Mars. Did water once flow here? And if so, was there life? After 68 days, Spirit reached this crater. It's 200 meters wide, rocky, sandy, and windblown. 3 weeks after Spirit, on the other side of Mars, the lander Opportunity rolled into this crater. It was a bullseye. At this site, Opportunity confirmed there had once been water. And at this crater, Opportunity found exposed dark rock that may have clues to the distant past. The rovers did well, but a new sort of lander is needed. It must be intelligent and highly mobile. It must return Martian samples to Earth. Eventually, of course, humans will do the collecting, on this planet of the god of war.